Bismillahirrahmanirrahim. Assalamu alaikum. I am Zishan. Complete operation and performance calculation of a thermal power plant is purely based on thermodynamics. In this video, we will be discussing about some very basic concepts of thermodynamics and terminologies related to thermal power plant. Subcooled liquid, saturated liquid and saturated steam, and superheated steam. All these are the terms that are related with the operation and performance calculation of feed water heaters, boiler, steam turbine, and condensers. Because in a thermal power cycle, the subcooled liquid is first converted into a saturated liquid and then into the saturated vapors and ultimately superheated in the superheater section of the boilers. The superheated steam is then fed into the steam turbine to do work, and ultimately it is condensed back to saturated liquid conditions in the condenser section of the cycle. And this whole process continues to complete the cycle. Steam quality or dryness fraction is of key importance when we talk about the efficiency calculation of the steam turbines, and more particularly for the low pressure turbines which are directly connected with the condenser. We will be also discussing about the isothermal, isentropic, isobaric and steam quality lines that plots over the temperature entropy diagram. So let's expand our discussion by having the overview of the major areas of this graph. This is the area that shows the subcooled or the compressed liquid region. This red line indicates the region of the saturated vapors, and the area on the right side of the curve is for the superheated steam region. All this area shows the superheated steam region. Inside the dome, there is a two-phase region. We can also call it as a wet steam region, because both the liquid and the vapor exist in equilibrium with each other. We will be discussing about all these terminologies through this simple example. Now let's have an overview of the isobaric, isothermal, isentropic lines and steam quality lines over this temperature entropy plot. The isobaric lines are those lines in which the pressures remains constant throughout the process. In the temperature entropy plot, isobaric lines follows this type of pattern. This is the pattern followed by the isobaric lines. I have plotted three lines here just to show or to clear the concept that the curves in the top of the dome shows the high pressure lines and the bottom of the curve shows the low pressure lines. So we can say that as we move from the bottom of the dome towards the top, the pressure increases. Isothermal process is that process in which the temperatures remains constant throughout the process or operation. And similarly, for any value of the operation, if we are moving in the straight line in the horizontal direction, the temperature will remain constant, and this process will be called as isothermal process. Isentropic is that process in which the entropy remains constant. It means that there is no increase in the entropy of the system. So as we can see that the entropy has been plotted over the x-axis, if we draw a vertical line over the plot, that shows the isentropic process because the entropy will remain constant throughout this line. So this process will be called as isentropic process. Now let's discuss about the pattern of the steam quality lines inside the dome. As we move from the saturated liquid line towards the saturated vapor line, the steam quality increases. These are the steam quality lines. Now let's expand and discuss all these terminologies and concepts that we have discussed so far through example of a piston-cylinder arrangement, in which the water has been placed at a temperature of 20 degrees centigrade, and this arrangement has been placed in a normal atmospheric condition with the pressure of 1 atmosphere being acting on the face of the piston, and the weight of the piston is also constant. The heat at constant rate is also being applied or been absorbed by the system. The same pattern has been plotted on the temperature entropy diagram. The state 1 indicates the temperature of 20 degrees centigrade and a pressure of 1 atmosphere. As the water in the system is absorbing heat, so the temperature of the water will increase, but the pressure will remain same throughout the process. So the temperature of the water will be increased from 20 degrees centigrade to 100 degrees centigrade. This is the condition at which the subcooled liquid has been converted into a saturated liquid condition. Now water has attained the temperature of 100 degrees centigrade at the pressure of 1 atmosphere. At this condition of 100 degrees centigrade, the water is still as liquid. Further addition of heat into the system will increase the tendency of this liquid to convert into the vapor state. So the liquid at this stage, which has the tendency to change its phase, is called as the saturated liquid. At this point, the boiling will start. Once the boiling starts, the temperature of the liquid will remain constant, but the liquid will start to convert into the vapor phase. This has been represented by the process 2-3. In this beaker, the blue color indicates the saturated liquid, and a small portion of the red part indicates the saturated vapor state. Upon further absorbing heat, the saturated liquid has been further converted into the vapor phase, and at the stage 3, both saturated liquid and vapor are present in the equal volume inside the system. From the phase 1 to the phase 3, specific volume and entropy of the system is been increasing. Upon further addition of the heat from the stage 3, we can see that almost 80% of the liquid has been converted into the vapor state, and remaining 20% of the liquid has been left inside the system. As the system is absorbing heat, so at the stage 4, all of the liquid has been converted into the vapor phase. Now let's discuss the concept of the steam quality. In between the dome, we have said that it is called as the two-phase region or a wet steam region. Upon moving from point 2 to point 2-3, 20% of the liquid has been vaporized and 80% of the liquid has been left inside the system. So we can call it as it has the steam quality of 20%. At stage 3, the 50% of the liquid has been vaporized and 50% of the liquid has been left behind. It has a steam quality of 50%. At stage 3-4, the 80% of the water has been vaporized or converted into the steam region or the vapor phase, so it has the steam quality of 80%. So we can see that as we are moving from point 2 to point 4, the steam quality is been increasing by the addition of heat. We can also reverse this process. If we remove the heat from the system, the steam quality will reduce and this vapor phase will start to condense back to the saturated liquid. The same can be possible by varying the pressure of the system. Now at the stage 4, all of the liquid has been converted into the vapor phase, so we can call it as a pure steam. The steam quality at stage 4 is 100%, which is the pure steam present in the system. The saturated vapors present at the stage 4 continues to absorb heat. So at this stage, these saturated vapors will be converted into the superheated region at the temperature of tentatively 250 degrees centigrade. Now let's discuss the concept of a subcooled system, saturated and a superheated system in a more easy and simple way. The temperature of the system is constant at 100 degrees centigrade as we are moving from the point 2 to point 4. Let's draw a simple line here. So in other words, the saturation temperature can be defined as the temperature of the system in which both the liquid and the vapor phase are in equilibrium with each other. It's called as the saturated temperature, and the corresponding pressure will be called as the saturation pressure. the saturation temperature will change if we change the pressure of the system. So 100 degrees centigrade will be called as the saturated temperature of the system at that particular pressure. At the state 1, the temperature of the system is 20 degrees centigrade, which is less than the saturation temperature. So when the temperature of the system is less than the saturation temperature at that particular pressure, it will be called as a subcooled system. For the concept of the superheated vapors, let's discuss the condition of the system at the stage 5. At the stage 5, the temperature is tentatively around 215 degrees centigrade. So we can call the system at the state 5 is in the superheated condition because it has the temperature higher than the saturation temperature at the pressure of 1 atmosphere. So concluding the discussion, if the temperature of the system is less than the saturation temperature at that particular pressure, it will be called as a subcooled system. And if the temperature of the system will be higher than the saturation temperature at that particular pressure, that system will be called as the superheated system. So this brings to the end of the session, and it had covered everything that I want to say. Thank you very much for your attention, listening and time. In the upcoming session, we will be discussing and learning to draw the same temperature entropy diagram in the simple application of Microsoft Excel. We will also learn to draw the plot of a simple thermal power plant and the Rankine cycle over that temperature entropy diagram. So keep connected for more stuff like that, and with this, Zishan signing off. Thank you.